Welcome to the first lesson of the 10th module, which is on springs. Now, so long we have looked into the aspects of the strength, the stiffness and the stability on the members, wherein we have evaluated the stresses, we have evaluated the deflections and also we have looked into the stability aspect of the member. Now, we are going to discuss on a special topic on which we will make use of the formulae which we have derived, and we will look into that how to calculate the stresses in a member called spring. Hence, it is expected that once this particular lesson is completed, one should get an idea about the different types of springs that are commonly used. That means, we will look into that what we really mean by spring, and then what are the different types of springs that we come across, and what are the types of springs that are commonly used. One should be able to understand the concept of stress and deflection in closed coiled helical springs. Now, as you can see that we have taken a specific name called closed coiled helical spring. Now, we will look into the different types of springs, and we are not going to discuss all the types in this particular course. We will be restricting ourselves specifically to the helical springs, and we will look into those aspects of helical springs where how to evaluate the stresses in the springs. And one should be able to evaluate stresses and deflection in closed coil helical springs. The scope of this particular lesson therefore includes, well, the recapitulation of previous lesson. Now, as we have seen that in the previous module we have discussed about the stability of the columns, and in the previous lesson on stability of columns I have given you some questions. We will be discussing the answers of those questions, and to that extent we will recapitulate the previous lesson. Also, we will look into the different types of springs that are commonly used, and this particular lesson includes the derivation of formulae for evaluation of stress and deflection in closed coil helical springs. In fact, we will make use of the already derived formulae for the members, where we have seen that how to calculate stresses for different types of forces such as axial force or the shear force or the bending moment or the twisting moment. We will try to make use of that and see that a spring is subjected to what kind of stresses because of the application of the force, and we will try to combine the effect of these forces and thereby the stresses in a spring. Also, we will look into some examples for the evaluation of stress and deflection in springs. Well, then before we go into the discussion for the springs, let us look into the answers of the questions which were posed last time. Now, the first question which was given was, what is the effective length of a cantilever column? Now, as I have told you that the previous lesson was on stability of columns, and you had seen that how to evaluate the critical load using Euler's formula, which we have called as Euler's critical buckling load formula, which was given by Leonhard Euler. And we have seen that if a column member is of having different support conditions, like if both ends are hinged, or if you have one end fixed other end hinged, or if you have fixed condition, or if you have a cantilever member where one end is fixed and other end is free, then how do we evaluate the critical buckling load in such members? Now, the question is that what is the effective length of a column member which is a cantilever, means is fixed at one end and free at the other, and the actual length of the member is L. Now, as we have seen, if we use Euler's critical buckling load formula, then P critical is equals to pi square EI over L square. Now, in case of a member which is fixed at one end and free at the other, the critical load evaluation comes as pi square EI over 4 L square, and this we have seen in the derivation of the previous lesson, wherein we have derived this particular expression. Now, if this term 4 L square, if we write in a square form, it is 2 L square, and thereby 2 L is equivalent to this term LE. So, the effect this we have called as effective length. So, effective length LE is equals to twice the actual length, and as we have seen that for different support conditions the corresponding term, the coefficient of L varies, and we have designated that as KL, the L effective as equals to K times L, and this parameter K changes with the support conditions, and for cantilever case the value of K is equals to 2. So, the effective length for a cantilever column is equals to twice the actual length, and the effective length coefficient K is equals to 2. So, this is the answer for the first question. The second question is, what is intermediate column and how is it different from long or short column. Now, if you remember, we had discussed the aspects of short column, the aspects of long column, and then we had defined what is intermediate column. Now, coming back to the discussion again with the Euler's critical load, the critical stress, as we have seen that PCR is the critical load, is equals to pi square E I over L E square, and I we had represented in terms of the area, cross sectional area, and the radius of gyration A r square, and thereby PCR by A, if I divide by A, this gives us sigma critical. So, critical stress is equals to pi square E, and I if we take in the denominator we have L E by r square. So, pi square E by L E by r square is the critical stress. Now, if L E by r becomes very small, then the value of sigma CR will be large, and smaller value of L E by r indicates that the lower height of the column member, and thereby that refers to a short column. Now, the stress becomes higher means that if it goes beyond the yield stress, the material is going to yield. So, it has really no meaning saying that the stress is much higher. So, we restrict ourselves to the limit of the yield stress. So, when the stress level goes beyond yield stress, that means the member fails by yielding. So, we categorize those group of columns as the short column, where L by R or L E by R is such that it produces a stress which is above the critical stress or sigma yield stress, where here in this particular case the critical stress is the yield stress, and the columns which come under that group we designate them as short column. Now, if L E by R becomes larger, then the stress becomes lower. Now, the question is, up to a limit of the stress limit of the up to proportionality, if we restrict ourselves to that limit, then the L E by R which we get for a particular member, corresponding to that we can find out the stress, and that stress will be somewhere below this stress limit at the proportionality limit state. So, the columns which are governed by this particular expression of given by Euler are valid when the stress is lower than the proportionality limit stress. So, the short column are the one which goes beyond the yield stress, and the long columns are the one where the stresses are governed by this expression, where the critical stress is limited up to the stress at the proportionality limit. Now, in between these two stages, in between the state of short column and in the state of long column, we get a set of columns which we designate normally as the intermediate column. So, intermediate columns are in fact is the one which may fail by the combination of the yielding and the buckling. Now, as we have seen that in case of short columns it fails by yielding or crushing, and in case of long column it fails by buckling. Now, intermediate columns they fail by the combination of these two, by yielding and the buckling, and they are in a particular range between this short column and the long column, and those columns are called as intermediate columns. And for intermediate columns, if we try to find out the critical load using Euler's formula, it will not give you the correct result. So, the last question was that what is Rankine constant, and it is dependent on which parameters. Now, as we had seen that for such intermediate columns where we cannot apply Euler's critical load formula for the evaluation of critical load, Rankine had proposed one empirical relationship for evaluating critical buckling load for such columns, which is given by this sigma y times A divided by 1 plus sigma y by pi square E into L E by R square, where sigma y is the yield stress of the material, A is the cross sectional area of the column member, E is the modulus of elasticity, L E is the effective length and R is the radius of gyration. Now, in this particular parameter, which is sigma y by pi square E, this is known as the Rankine's constant. And as you can see from this particular expression, here we have a parameter sigma y, which is the yield stress of the material, we have parameter E, which is the modulus of elasticity. So, basically Rankine's constant, as you can see, is dependent on the material properties, the modulus of elasticity of the material and the yield stress of the material with which the column member is fabricated. So, this is what is known as the Rankine's constant. Well, then having looked into these aspects or the answers to the questions which were given last time, let us look into the aspects which we are going to discuss today, which are the springs. Now, spring is an element which is defined as that this is an element which is used to achieve a flexible joint between two parts or bodies. Now, as you have seen earlier that the deformations are not desirable in structural element, or whenever we have looked into some structural element like beams or axial members or any other pressure vessels kind of a thing, we have looked into that we do not like to have deformations in the member, but there are some situations where we need to have deformations or where we need some amount of deformations to be introduced into the system. And to achieve these kind of deformations or flexibility, we introduce an element which we normally term as spring. Now, in the spring is an element where it is loaded, it undergoes movement either elongation or shortening, and once we remove the load, the element comes back to its original position, and the level of the working stresses in the spring material is rather high in comparison to the other structural materials as we use. Now, this is what is stated over here, that when flexibility in a mechanical system is desired, because this is what is needed, that we like to introduce some amount of flexibility, then we introduce this element which we call as spring. Or also that if we like to absorb some energy, many places members, structural members or mechanical systems, they are subjected to loads which are sudden loads. Now, if these kind of sudden loads act on structural members, the structural member may undergo large deformation, and thereby there could be stresses which goes beyond the yield value of the material. Now, there to absorb this shock loading or the impact loading, we introduce these kind of elements which we call as spring, and these spring elements can absorb the energy which are being imparted by the external load, and thereby it can undergo some amount of deformation and absorb that external loading shock. So, when flexibility is desired in a mechanical system, or you need to require the absorb the energy of a suddenly applied load, then we introduce spring so that we can achieve the desired result. Now, the different types of springs that are commonly encountered are leaf springs, the helical spring and flat spiral springs. There are other kinds of springs as well, but these are commonly used. Now, let us look into these different types of these springs. Now, leaf spring is a spring which is also known as carriage springs, which we can see in the form of which are used in the transport vehicles. You must have looked into in the vehicles, this form of springs are used, and basically here we have the plates, a number of plates are joined together to form this kind of springs, and this kind of springs can absorb the vibratory load that gets transmitted from the vehicles. And here this particular type of spring, as you can see, the plate, the top plate, which we call as a master leaf. Basically these plates are called as leaves, and that is why this name as the leaf spring. Now they are in a semicircular shape, and because of semi elliptic shape, and that is why this kind of springs are also designated as semi elliptic spring. So this top plate, as it is designated over here, is the master leaf. There are clamps which holds all the plates positioned here together, and there are clips here which we call as a rebound clip to keep the spring in position. We have another kind of spring which are helical spring. In fact, in this particular module we will be looking in details about these helical springs, and helical springs are commonly used to absorb shocks. As I have told you that the springs are used to have the desired flexibility in a mechanical system, or we introduce springs to absorb shocks or the impact of the loads which come suddenly on the member. Now helical springs are the springs which are generally used for absorbing such shocks. You must have looked into that when a railway wagon comes into a platform. In a platform you have those buffers where the wagon comes and hits and then stops. Now when it comes, the wagon comes in a speed and hits on that buffer, naturally it imparts some amount of energy on those buffers, and the buffers are provided with the springs which can absorb this shock. So this is one of the examples where we use these helical springs, and there are of course other areas where helical springs are used. Now helical springs are of two types. They are closed coiled helical spring, and other one is open coiled helical spring. Now we will be looking into these two categories in greater detail. Now in this particular lesson we will be concentrating on the closed coil helical spring, and subsequently we will look into the aspects of open coil helical spring. Now other than a leaf spring and the helical spring, another kind of spring which we are commonly encounter is the flat spiral springs. You know, in the toys or in clock mechanisms, these kind of springs are used. Now this particular spring is in one plane, and they are wound in such a way that we apply a torque at one end and other end is hinged. So thereby the whole spring is in a taut position, and the cross section of this particular spring material is something like a rectangular one having a thickness T and depth D, and this particular kind of spring, they are in one plane. In one end of the spring is hinged and the center of it is applied with a torque, and then they are kept in a taut position, and in the these particular springs are used in mostly in the toys or in clock mechanisms. Now apart from those springs which are very commonly used, other kinds of springs are there where which are used in some specialized cases, and these springs are termed as Belleville spring or disc type of spring, ring spring or volute spring. So these are the different kinds of the springs which are seen, but you know, they are occasionally used in some special cases, and we are not going to go into the details of these. In this particular course we will be restricting ourselves to the helical springs only, and we will look into the two types of helical springs, as I have said, that closed coil helical spring and the open coil helical spring. We will look into how to evaluate the stresses in those kinds of springs if they are subjected to loads. Well, let us look into the behavior or the characteristics of closed coil helical springs. Now why we call this as closed coil helical spring? Basically, as you can see, this a wear which is forming a helix, we call that as a helical spring. Now when these wears are wound in such a way that each turn of this helix, they are virtually in the same plane. So that is what is indicated over here, are closely wound, so that each turn of the spring, this is important, that each turn of the spring virtually lies in one plane, and since they are very closely wound, we call this kind of springs as the close coiled helical springs. Now, let us look into how do we calculate the stresses in such closed coil springs. Now, if a closed coil spring is subjected to a load P as indicated over here. Now, the ends of these closed coil springs are provided with some forms, so that they are connected with some supports or some loads can be applied at these particular ends. So, several kinds of mechanisms are formed at the end, either in the form of a hook or a flat end which can be connected to a particular member, where we can apply a load P in this system. Now, supposing if we take a part of it, if we cut across and take a free body of this particular spring. Now, these turns which we normally call as coils, that this particular spring, they are having several coils along its length. Now, if we look into one of such coils, where we have the load P acting into the member, and thereby this is the load P. Now, if we transfer that load in the section of the member, this P gets transferred along with a moment, and this particular moment here is a twisting moment T. Now, in this particular coil, if you look into that, we have one wire which is having a diameter D. Now, if we look into a plan view of one of such coils, say this is the circular form, and this is the radius R up to the center line of the wire, and this R is the, we call this as a mean radius of the spring. R we call as mean radius of the spring, and small d is the diameter of the wire with which the spring is formed, and capital D is the diameter of the spring, of the whole spring coil, as it is indicated over here. It is from the center of this dia to the center of this dia of the wire, which is designated as capital D. Now, if you look into this action of these forces when it is transferred to this center of the wire cross section, where this load P is acting as a shearing force, and thereby it will produce a direct shear stress, and the twisting moment T, which is acting in this tubular section, or I mean in the solid circular section, will be producing a shearing stress, as we have seen earlier. As we have seen that if a tubular member is subject, a solid circular section is subjected to a twisting moment T, then you get the shearing stress. So, as you can see that if you consider the wire, the circular wire which is subjected to shearing force P, will produce a direct shear stress, and because of the twisting moment you will have a shearing stress component which is a function of the twisting moment. And here in generally in spring we consider the shearing stress, the direct shearing stress in the form of average stress, which is equals to P by A. So, the cross sectional area of this spring wire is pi d square by 4, where small d is the diameter of the spring wire and P is the shearing force that is acting in the wire. So, the shearing stress tau 1 is equals to 4 P by pi d square. Now, because of the twisting moment T, which is equals to P into R, we get another component of the shearing stress, which is 16 T by pi d cube. This we have seen earlier, that T by J is equals to tau by rho, and tau as we calculate is equals to T rho by J, and rho for a circular one is d by 2 and J is pi d 4 by 32, and thereby we get tau as 16 T by pi d cube. And the value of T, the twisting moment in this particular case, is equals to P times R, where P is the force which is acting through the axis of the spring, this we call as the axis of the spring, and R is the mean radius of the spring coil. So, P times R is the twisting moment that will be acting in the spring wear. So, if we replace T as P times R, so this becomes 16 P R by pi d cube. So, you see the total shearing stress that the wear will be subjected to is the combination of these two shearing stress, one is tau 1, other one is tau 2. So, we call this as the maximum shearing stress tau max is equals to 4 P by pi d square plus 16 P R by pi d cube. Now, this is from the direct shear stress and this is originating from the twisting moment. Now, if we take 16 P R by pi d cube out, we get a factor which is 1 plus d by 4 R, and this particular bracketed term we call as K, which we call as a stress concentration factor. Basically, if you look into the 16 P R by pi d cube is the shearing stress which is getting generated because of the twisting moment of magnitude P into R. So, the shearing stress which is getting generated because of the twisting moment is multiplied with a factor K, which we call as a stress concentration factor. Now, so this stress concentration factor, if you look into is equals to K and this is multiplied by the shearing stress 16 P R by pi d cube. Now, K as we have seen is equals to 1 plus d divided by 4 R. Now, R is the mean radius. So, twice R, so 4 R we can write as 2 into 2 R, and 2 R is nothing but as the diameter of the coil. So, this particular term capital D by small d, this ratio we define as spring index and designated as the parameter C. So, C is defined as the spring index, which is the ratio of the coil diameter to the wear diameter D. So, if we substitute for d by d as C, we get K as equals to 1 plus 1 by 2 C. So, this is termed as the stress concentration factor. Now, as we have seen here, while evaluating the stress concentration factor K, or while designating that bracketed term 1 plus d by 4 R as a K stress concentration factor, there we have accounted for the shearing stress because of the direct shear, which is in an average sense, and also we have not considered as such the curvature of the spring coil. Now, this particular aspects, the maximum value of the shearing stress as it can happen in that circular cross section, or if we take the curvature of the spring coil into account, this particular factor gets modified, and in 1940 A. M. Wall had proposed the modification of this particular factor, which we call as Wall correction factor Kw, and Kw is given by this particular expression. Now, when we need to evaluate the stresses precisely, we use this Wall correction factor Kw instead of K, which is 4 C minus 1 by 4 C minus 4 plus 0.615 by C. Now, having looked into that how to evaluate the stress, now, so we can compute the value of the stress if we know the amount of load a spring is subjected to. The load which will be acting through the axis of the spring, as we have seen just now, that will produce a direct shearing stress and a twisting moment into the spring coil, and the twisting moment eventually will lead to the shearing stress. So, we will have two components or two shearing stress, that is, one is from the direct shear force, another one is from the twisting moment. So, it is a combined action of these two shearing stresses or two forces, that axial force or shear force P and the twisting moment T, which is equals to P times R, will give you two stresses which are combined together to get the resulting shearing stress in the member. Now, when a spring element is subjected to axial load, it undergoes deflection or deformation. Now, we need to find out that how much elongation or compression, which we call in general as the deformation in the spring, it undergoes because of the application of the axial load P. Now, let us look into this, that if a member is a spring is subjected to a load P, then what happens? Now, as we have seen that the wear with which the spring is formed is subjected to a load P and a twisting moment T. Now, we consider a spring where the spring index is rather high. The spring index, as we have seen, C is equals to d by d, wherein the diameter of the coil is larger or the wear diameter is very small. Now, for such larger spring index or for springs with having larger spring index, if we consider a small element in the spring, let us call this as distance AB. Now, virtually this becomes like a straight length, that means you have a straight rod which is subjected to a twisting moment, and in this particular case we ignore the effect of the axial or the direct shear, the deflection that will be produced by the direct shear. We will be evaluating the deflection that will be caused by the twisting moment T. Now, if we look into this particular segment AB, say having a length dx, now because of the constant twisting moment T, which is equals to P into R, this is subjected to, this will produce the rotation, and the relative rotation between the two sections A and B, if we call that as d theta, then we can compute this value of the relative rotation d theta from T dx by Gj. As you know that T by J is equals to tau by rho is equals to G theta by L. So, theta for a smaller element, as we are looking into d theta, is equals to T L by Gj, and L here is the dx, length dx for this particular element AB. Now, if we think of that A is fixed and B is moving, so that means d theta will give the rotation of the segment AB. Now, because of this rotation of this segment AB, the point F of this load point will undergo a movement, and let us call this movement as Fd. Now, basically this movement will be in an arc length, but since AB is a small segment, we consider that Fd also will be small. So, that Fd is perpendicular to this length Bf. Now, this particular one is exaggerated over here in this figure. Now, this distance, so Fd can be written as Bf times d theta. So, we can write this as the value of Fd, this as equals to Bf, the distance Bf times d theta. Now, if we take the component of this Fd, one will have horizontal component, another one will be the vertical component. Now, this particular spring where we have considered one segment is producing one horizontal component Fe. Now, since this particular spring will have coils, a number of coils, and this horizontal component will be produced by each of these segments, eventually these horizontal diametrically opposite points in the spring, those horizontal components will cancel out. So, the components which will be remaining is the vertical one, and the vertical component here is the dE, the distance dE. Now, if we look into this particular triangle, which is FDE, this is F, this is D, this is E. So, in this triangle and the triangle ABC, if we look into these two triangles, then the dE divided by FD, this perpendicular to this hypotenuse, dE by FD is equals to BC by BF. So, this is what is indicated over here, dE by FD is equals to BC by BF. Now, as we have seen that FD is equals to BF times d theta. So, if we write that, then dE is equals to BC times FD by BF, and FD we write as BF d theta. So, BF d theta by BF. So, this is what is indicated over here. and the distance BC, as you can see, is nothing but equals to the radius, mean radius of this spring coil, and this is r. So, this particular expression becomes equals to r times d theta, and mind that this is the vertical component which is dE, and this is generated because of this segment which AB undergoing a twisting moment T. This we call as small deformation d delta. Now, if we sum up all these deformations in the entire spring coil, then we integrate these over the entire length of the spring, and so we integrate this r d theta. So, thereby we get the total deformation which we have designated as delta. This is equals to, in place of d theta, if we place T dx by Gj. So, T r by Gj will come out and integrate dx over the length will give you length L. So, delta, the total deformation that or total deflection that we get in the vertical direction, is equals to T r L by Gj, and as you know, the twisting moment T is equals to P times r. So, this becomes P r square by Gj, and the length L is the total length of the spring coil. Now, a spring which is having a number of coils, and one such coil if we take which is having a circular form having mean radius r, the length is twice pi r, and if we have n such turns, then n times twice pi r will give us the total length of the spring, and this is what is indicated over here. L is equals to twice pi r times n. N is the number of coil or number of turns we have in the spring. So, and J, as you know, is the polar moment of inertia of the wear of the spring, and the diameter of the wear is small d. So, this is pi d 4 by 32. So, if we substitute these values, we get the value of delta as equals to 64 p r cube n by g d to the power 4. So, this is the value of the deflection that we get in the spring, and mind that we have computed the value of this deflection considering the effect of the twisting moment only, and we presume that the effect of this direct shear in the deflection is rather insignificant, and thereby from this expression we arrive at a parameter which is quite important, which we call as spring constant and normally designated as small k, which is equals to P divided by delta, the load, axial load divided by the deflection that it undergoes delta, which is equals to G d 4 by 64 r cube times n. And as you can see, all the parameters G, D, R, N, they are basically the parameters of the spring coil. D is the diameter of the wire with which the spring is made, R is the mean radius of the spring coil, N is the number of turn, and this particular parameter spring constant is of importance because that gives us the behavior of a spring, or the behavior of a spring can be judged from the spring constant value. So, if we know the spring constant from which if we like to permit a certain deformation in the member, we know how much load that can be applied on the spring. So, spring constant parameter is one of the important parameter for a spring. When you use such spring, we use this particular parameter for characterizing the behavior of the spring. Well, then having looked into the aspects of the stresses that are generated in a spring and how to evaluate the deflection of a spring because of the load, let us look into the examples, some of the examples through which we can evaluate these parameters. Now, the example problem here is a closed coiled helical spring is made of a wire of diameter 25 millimeter. That means, the smaller d is equals to 25 millimeter. With this, the closed coil helical spring is formed. The spring index value is given as 8, and as you know, spring index C is equals to capital D by small d, and the value of that spring index is equals to 8. You will have to find out the number of turns those are required and maximum allowable load if the allowable shear stress is 100 megapascal, and elongation of the spring is limited to 40 millimeter. The value of the shear modulus G is given as 80 gigapascal. So, what you need to do is that you will have to find out the number of turns, that means the value of N, and the maximum allowable load, the P, that can be allowed on this particular spring. So, if we calculate these values, the values as I said given are diameter of the wear, which is equals to 25 millimeter, and the spring index C is equals to d by d, which is equals to 8. So, from these we can evaluate the diameter of the spring coil, which is equals to 200 millimeter, and the mean radius is equals to 100 millimeter. So, from the expression of the shearing stress, as we have seen, the maximum shearing stress is equals to K times 16 PR by pi d cube, where K is the stress concentration factor and is given by this expression as 1 plus 1 by twice C, and C being 8, this is 1 plus 1 by 16, and this gives us a value of 1.0625. Now, if we substitute all these values in the expression for the stress, because stress is to be limited to 100 megapascal. So, here if we substitute all these values, this is 16, P R is 100 and pi 25 cube, D is 25, and the factor K is equals to 1.0625. Then the value of P from this expression comes as 2888 Newton. Also, it is stated that the maximum value of the deflection of the spring is restricted to 40 millimeter. So, if you restrict the deflection of the spring to 40 millimeter, and from the expression of the deflection which we have seen, which is equals to 64 P R cube times N by G D to the power 4, where N is the number of turn. So, from this we get N is equals to 40 for the delta max, G is shear modulus, which is 80 gigapascal. So, 80 times 10 to the power 3, so much of megapascal, times D is 25. So, 25 to the power 4 divided by 64, P as we have calculated now is equals to 2888, and R is equals to 100. So, 100 cube, and this gives us a value of 6.8. So, if you round it off, the number of turns you need are 7. So, the spring with which I mean a wear of diameter 25 millimeter has been used to form can carry a load of 2888 Newton, 2888 Newton, and if we like to limit the displacement or the deflection of the spring up to 40 millimeter, then the number of turns those are required are 7. Now, let us look into another example. This is an interesting problem in which a wagon weighing 50 kilonewton moving at a speed of 8 kilometer per hour has to be brought to rest. Now, springs made of wear of diameter 25 millimeter with a mean diameter of 250 millimeter of the coil and with 24 turns are available. So, these are the springs which are available. They are made of wear of 25 millimeter diameter, and the mean diameter of the coil is 250 millimeter, and there are 24 turns in that particular spring. You will have to find out that how many number of such springs are required, so that the wagon can be brought to rest with a compression of 180 millimeter. That means, the maximum deformation that you can allow on the spring is equals to 180 millimeter. The value of the shear modulus is given as G equals to 84 gigapascal. Now, here as you can note that the wagon which is moving at a velocity has to be brought to the rest. Now, when it goes and hits into the buffer, the energy, the kinetic energy of the wagon is transferred into the energy that can be absorbed by the spring. So, we need to find out that if a force is applied on the spring, and if we can allow a maximum compression of as it is given 180 millimeter, then what is the work done by those springs to absorb the thrust or the load which is imparted on those springs by the wagon, and then the wagon can be brought to the rest. So, if we compute these values of the kinetic energy of the wagon, which is equals to half mv square, as you are aware of that the kinetic energy of this wagon is equals to half mv square, where m is the mass of the wagon and v is the velocity with which it is moving. Now, as it is indicated over here that the velocity of the wagon is 8 km per hour. So, if you reduce it to or you convert it in terms of meter per second, 8 km is 8000 meter divided by hour is converted in second. So, this gives us 2.22 meter per second, and the weight of this wagon is given as 50 kilonewton. So, m is equals to w by g, and g is equals to 9.81 meter per second square. So, this is what has been divided, w divided by g, and 50 kilonewton. So, 10 to the power 3 is multiplied with to get convert it to Newton, and 2.22 square is the v square. So, this gives us a value of 12.6 into 10 to the power 6 Newton millimeter. Now, let us look into that. If we have to limit the deformation of the spring to 180 millimeter, then what is the load that can be taken by the spring? Now, from the expression of the deformation or the deflection, that delta is equals to 64 p r cube n by g d to the power 4, we can see that we can evaluate the value of p, because the value of r, the value of the diameter is given, the mean diameter of the spring is equals to 250 millimeter, thereby the radius is 125 millimeter, and the number of turns given for the spring is 24, and the diameter of the wear with which the spring is formed d is equals to 25 millimeter. So, with these values, if we substitute over here, we have p is unknown, r is equals to 250 by 2, which is 125 cube, and n is 24. The shear modulus g is given as 84 gigapascal. So, 84 times 10 to the power 3, so much of megapascal, and diameter d is 25. So, 25 to the power 4. So, this gives us a value of p which is equals to 1968.75 Newton. So, this is the value of the load that the spring or this load can be applied to the spring, so that the deflection criteria is satisfied. And as I said that the kinetic energy of the wagon is to be absorbed by the springs by applying that load and allowing that deformation, which we call as the work done by the spring. That means, to achieve or to have a maximum deformation of the spring up to 180 millimeter, the load, as we can see that we can apply P, which is 1968.75 Newton. So, this load will do some amount of work in pushing the spring up by 180 millimeter. So, the work done by the spring is equals to half P times delta. So, P is as we have seen over here is 1968.75, and the delta or the deformation is equals to 180 millimeter. So, this gives us a value of the work done by each of the spring is 0.18 into 10 to the power 6 Newton millimeter. And as we had seen that the kinetic energy of the wagon is equals to 12.6 into 10 to the power 6 Newton millimeter. So, this is to be brought to the rest. So, the number of springs that we need is equals to this kinetic energy divided by the work done by each of these springs. This will give us a number 70. So, these many springs are to be used, so that the wagon can be brought to the rest by absorbing the energy which is being imparted by the wagon. Now, we have another example where it says that a closed coiled helical spring is made out of wire of 6 millimeter diameter with a mean diameter of 80 millimeter. Now, what axial pull will produce a shear stress of 140 megapascal. So, you will have to find out what axial pull that you can apply, that means the value of P can be applied. If the spring has 20 coils or 20 turns, then how much the spring will extend under this pull, that means you will have to find out the deformation delta, and what work will be done in producing this extension. The value of shear modulus G is given as 80 gigapascal. Now, the values given are the diameter of the wire with which the spring is made is 6 millimeter, the mean diameter of the spring coil is 80 millimeter, thereby the spring index C is equals to capital D by small d, which is equals to 80 by 6 gives us a value of 13.33. Now, if we use this value of the spring index, then the stress concentration factor K, as we have seen, is equals to 1 plus 1 by twice C, and C being 13.33, this value of K comes as 1.0375. Now, it is stated that the maximum shearing stress that can be imparted or that is allowed is equals to 140 megapascal. So, what will be the load corresponding to that? So, if we substitute in the expression for the stress is equals to the stress concentration factor K multiplied by 16 PR by pi d cube. So, R, since the diameter of the coil is 80 millimeter, the R is 40 millimeter and the diameter of the wire is 6 millimeter. So, this is pi times 6 cube. So, this gives us a value of P which is equals to 143 Newton, and the value of the deformation of the deflection delta, as we have seen, the expression for the delta is equals to 64 PR cube by PR cube times n divided by G d to the power 4, and we have evaluated the value of P which is equals to 143 Newton. R, as we have said, is the radius of the mean radius of the coil, which is 40 millimeters, so 40 cube, and number of turns in the coil is equals to 20. The shear modulus value G is 80 gigapascal converted to a megapascal, so 80 times 10 to the power 3, and D is the diameter of the wire which is 6 to the power 4. This gives us a value of delta as 113 millimeter. So, the load which can be imparted on the spring coil is equals to P, which is 143 Newton, and the deformation that occurs because of this load P is equals to 113 millimeter. So, the work done by this particular load is equals to half P times delta. This is equals to 8079.5 Newton millimeter. So, as you can see in this particular spring, then you can apply a load P is equals to 143 Newton, and thereby when you apply that load in the spring coil, it can undergo a deformation of 113 millimeter, and then the work done by this, by applying this load and deforming the spring to 113 millimeter, that is 8079.5 Newton millimeter. Well, we have another example where it is required to design a closed coil helical spring. We will have to design the spring. Now, the parameters which are desired, which will deflect 10 millimeter under an axial pull of 100 Newton with a shear stress, allowable shear stress of 90 megapascal, and the spring is to be made from circular wire, and the mean diameter of the coil will be 10 times the diameter of the wire. So, it is stated that the capital D is equals to 10 times the small d, or spring index is given as 10. So, you will have to find out the diameter and the length of the wire, so that the spring can be formed out of it. G is given as 80 gigapascal. Now, here what is given is the load P 100 Newton and the shearing stress allowable is equals to 90 megapascal. Also, the maximum deflection that is allowed is equals to 10 millimeter. Now, it is given that the spring index C, which is the ratio of the capital D to the small d, is equals to 10, or the mean diameter of the coil is equals to 10 times the diameter of the wire. Now, from the spring index C, we can compute the value of K, which is 1 plus 1 by twice C, and this gives us a value of 1.05. Now, from the expression of shearing stress, tau is equals to K times 16 PR by pi d cube, limiting the shearing stress to 90, we can find out K is 1.05, P is 100 Newton, R, capital R is half D, which is 5 times D, and small d is the parameter which we will have to evaluate. So, from this expression all the parameters are known except D, and this value of D comes out as 5.45 millimeter. So, the diameter of the wear that is to be used for forming the spring is 5.45 millimeter. Now, from the expression of the deflection, the delta equals to 16 PR cube n by g d to the power 4. If we limit the deflection to 10 millimeter, and since all other parameters are known except the number of turn n, we can compute the value of n, and n comes out as 5.45 from this expression for the diameter of the wear as 5.45 millimeter. So, if we use a round figure of this number of turns, which is 6, then as we have seen, the length of the wear that will be required, that one turn is of length twice pi r, where r is the mean radius and n is the number of turns. So, radius here, the mean radius is 27.25 millimeter, and 6 turns if we take, then the length of the wear which we need is equals to 1027.3 millimeter. So, the diameter of the wear which we need is 5.45 millimeter, and the length of the wear which we need is 1027.3 millimeter for forming this spring. Hence, to summarize, in this particular lesson we have looked into aspects of the previous lesson through our question answers. Also, we have looked into the different types of springs that are commonly encountered. We have looked into the derivation of formulae for evaluation of stress and deflection in closed coil helical springs, and also we have looked into some examples for evaluating stress and deflection in closed coil helical springs. Now, these are the questions given for you. What is meant by spring index? What are the different types of stresses that closed coil helical springs are subjected to, and how do you define the stiffness of a closed coil helical spring? Now, answers to these questions will be given to you in the next lesson. Once you go through this particular lesson, you should be in a position to answer this, and we will be looking into the aspects of the open coil spring, helical springs in the next lesson. Thank you. Welcome to the second lesson of the 10th module, which is on springs part 2. In the previous lesson of this particular module, we have looked into the aspects of different kinds of springs. We have seen that what are the different types of springs and how they are used. Now, also we have discussed a special type of spring which we have called as helical springs, and as you have seen that helical spring is of two types. One is called as closed coil helical spring, another one is open coil helical springs. Now, in the previous lesson we have discussed about the closed coil helical springs, and we have looked into how the stresses and the deflections are induced in the springs when they are loaded. Now, in this particular lesson we are going to discuss about